Hello, AP Chemistry students. We're now at Unit 9, Part 1, and that means that we have arrived at the final unit of AP Chemistry. And this lecture is going to cover the other state functions, which is going to be sections 9.1 through 9.5. So our learning objectives here are to identify the sign and relative magnitude of the entropy change associated with a chemical or physical process, to calculate the entropy change for a chemical or physical process based on the absolute entropies of the species involved in the process, to explain whether a physical or chemical process is thermodynamically favored based on an evaluation of delta G, to explain in terms of kinetics why a thermodynamically favored reaction might not occur at a measurable rate, and then to explain whether a process is thermodynamically favored using the relationships between K, the equilibrium constant, delta G, and the temperature. So before we get into it, I want to review and introduce a few important ideas about thermodynamics. So in Unit 6, we've already studied thermodynamics a bit, learning about energy in chemical reactions. And in that unit, we defined something called standard state conditions, which is a normalized set of conditions that is notated with this little degree symbol. And this usually means that in the substances involved, the gases are all 1 atmosphere, the liquids and solids are completely pure, all of the solutions are 1 molar, the energy of formation of pure substances like oxygen or like a pure metal are 0 kilojoules per mole, and the temperature, unless notated otherwise, is 25 degrees Celsius or 298 Kelvin. So next I want to introduce the idea of a thermodynamic state function. While I haven't used this terminology before, we have studied one of these in a lot of detail so far, which is delta H, which represents the enthalpy change, whether or not heat is released in a reaction and is exothermic, or heat is absorbed in a reaction and is endothermic. Now, if you recall, delta means final minus initial. So the whole idea behind a state function is that it's a value and its properties do not depend on the path by which the system arrived at its present state. What that means is, say you're going from A to B, either we can go in a straight line or we can go in a curvy line, but the difference between B and A is going to be the same in either case. So like the delta distance between B and A in both of these diagrams is the same. So it doesn't really matter the mechanism that gets you from your initial state to your final state. What matters is the difference between those two states. So the other two state functions that we're going to be talking about today are delta S, which represents the entropy change, which is an increase or decrease in disorder, and delta G, which is the free energy change, which is the increase or decrease in energy available to do work in the physics sense, and it determines the overall favorability of a reaction to occur. So we're going to talk a lot about both of these. So if those explanations don't make sense now, don't worry about it. All right, and just another thing that is sort of important here is the laws of thermodynamics. So the first law of thermodynamics states that the energy of the universe is constant. That energy can be neither created nor destroyed. So while energy can be converted in a chemical or physical process, the total energy will always remain constant. And you might also know this as the conservation of energy. Now, the second law of thermodynamics, which we haven't really talked about before, I guess we kind of did in equilibrium, but if a process is favored in one direction, then it can't be favored in the reverse direction. And that an increase in entropy, aka disorder, promotes favored reactions. And the entropy of the universe is always increasing. So the chaos and the disorder of the universe is always increasing. Things are always going to want to get messier and more spread out and less ordered. And speaking of that, what takes more energy? Knocking down a tower or putting it back together? And which of these processes do you think is thermodynamically favored? We are going to go into detail what exactly that means in a bit. And which state here is more disordered, the tower built up or the tower fallen down? Well, in this case, a chemical or physical process that increases the disorder is favored in terms of thermodynamics. And that's because making something ordered, like stacking all these bricks into a wall, takes a lot more energy than undoing that order if you were to just kick it all over in a pile. And going from figure A to figure B here would be considered an increase in entropy, an increase in the disorder of the system. And entropy itself is defined, like I said, as a measure of disorder or randomness, and is represented by S. And the more disorder, the higher the absolute entropy value. And this is all based off of the idea that zero absolute entropy is defined as a solid crystal at 0 degrees Kelvin. So why that in particular? Because crystals are highly ordered structures. So crystals are not disordered at all. And 0 degrees Kelvin, absolute zero temperature, would indicate no kinetic energy or movement of particles. So everything is ordered and still. It's like a perfect ordered system. But technically, 0 Kelvin can't actually be reached. You can only asymptotally reach 0 Kelvin, which means that anything in the universe actually does have a positive entropy value. And there's no such thing as negative absolute entropy. And the standard entropy change, which is notated as delta S, and remember this degree symbol means standard conditions, describes the difference in absolute entropy between the products and the reactants. So a positive delta S is going to indicate an increase in disorder, while a negative delta S is going to increase the order of the system, or a decrease in the disorder. And you'll notice this formula here to calculate delta S. It's the sum of the absolute entropies of the products minus the sum of the absolute entropies of the reactants. And this looks really similar to the equation we used for the enthalpy of a process. And that is an important thing to note here, because all of the state functions are going to have a formula like this, where the overall delta whatever is going to be the sum of the delta whatever of the products minus the sum of the delta whatever of the reactants. Now, to look at an example of this, if you were to think about a solid ice going to liquid water, that's usually going to be an increase in disorder, because here you have an ordered crystal of water molecules, and they all separate and they all start moving around doing their own thing. So that was an increase in disorder. So our final state is more disordered than our original one, which would be a positive delta S. So here we notate that delta S is greater than 0. So some important basic principles of entropy. Liquids are always going to have a higher entropy value than solids. Obviously, liquids are more disordered than a solid. And then gases are going to have a higher entropy value than liquids. So the further you go up in the state of matter hierarchy into more energetic states of matter, the entropy is going to increase as well. Also, particles in a solution have higher entropy than a solid. So if you have like a sugar cube, the sugar molecules in a solution, in like a cup of coffee or a cup of tea or something like that, are going to be more disordered than they were when they were stuck together as a solid. Also, if we're looking at a gas phase reaction, 2 moles of a gaseous substance are going to have higher entropy than 1 mole. So if the moles of gas change in a chemical reaction, we can also use that to figure out how the entropy of the reaction is changing. And just as an overall idea, entropy is going to increase as the temperature increases. And this is due to a wider range of kinetic energies available at higher temperatures. If you recall when we looked at the Boltzmann diagrams before, where we had those sort of bell curves that showed all of the possible kinetic energies of something at a certain temperature, you might remember that as we increased the temperature of the system, that bell curve kind of widened to show a higher range of available kinetic energies for the particles at that temperature. And delta S and absolute entropy S have units of joules per mole per degree Kelvin. And you'll note that the other state functions that we've studied and will study will be just kilojoules per mole. So this one is on like a different order of magnitude. We're usually talking about smaller energies when we talk about entropies. So we use units of joules. And there's also a Kelvin unit attached to this because, like we mentioned here, entropy is highly correlated to temperature. So there's always going to be a temperature factor with our entropy. So let's look at a couple examples and estimate if our delta S is going to be positive or negative. Remember that positive means an increase in disorder and negative means a decrease in disorder or an increase in order. So we have iron solid becoming iron liquid. We have solid salt becoming aqueous salt. We have gaseous carbon dioxide becoming solid carbon dioxide. We have two hydrogen molecules interacting with an oxygen molecule to make two water molecules. And then we have two BrCl becoming a bromine molecule and a chlorine molecule. So in the first example, iron solid becoming iron liquid, that is going from a lower energy state of matter to a higher energy state of matter, and a more ordered state of matter to a more disordered state of matter. So that's always going to be a positive delta S value. Similarly for salt becoming aqueous, this is salt dissolving. It's going from a solid salt crystal to individual ions in solution that are going to be surrounded by water molecules. This is a more disordered state. So this is also going to be an increase in entropy. Carbon dioxide gas going to carbon dioxide solid. Now this is a decrease in energy for the state of matter. So this is going to be a decrease in disorders or an increase in order. And that's going to be correlated with a negative delta S. Here we have two hydrogen molecules interacting with an oxygen molecule to make two waters. Here, everything is in the gas phase, so everything's in the same state of matter. So we're going to defer to the number of particles. Here we have 3 moles of gas becoming 2 moles of gas. So 3 things are kind of coalescing into 2 things, which means that we are getting more ordered. So that's why this is a negative delta S. And then lastly, similarly, we have all gases. We're starting with 2 moles of gas here, making 2 moles of gas here. And this one, delta S, is actually going to be 0. It's not going to be positive or negative because we're staying at the same energy state of matter. And the moles of gas that we end up with and the moles of gas that we started with are the same. So now let's try a practice example of calculating delta S using absolute entropies from a table. And this is going to be exactly the same like we did it when we did the enthalpy calculations from before. So we have our water molecules that are being made by the hydrogen and oxygen combining, and we could see that we can find those on the chart. So hydrogen here is 130.7 joules per mole per degree Kelvin. Oxygen is here, 205.2, and then water is over here at 70. So I could set this up. The sum of the absolute entropies of the products minus the sum of the absolute entropies of the reactants. So we have 2 times 70, which was our value for water, minus 2 times 130.7, which was our value for hydrogen, plus 205.2, which was our oxygen value. And then overall, we get negative 327 joules per mole per degree Kelvin. And this makes a lot of sense because the moles of the gas are decreasing. We're going from 3 moles of gas to 2 moles of gas. And this actually agrees with the estimate that we made earlier just by looking at the chemical equation. So next we're going to talk about Gibbs free energy, also known as just free energy. And this is represented by G. And it measures the thermodynamic favorability. So delta G, the change in Gibbs free energy, is going to describe whether a process will occur without energy input, meaning it's either spontaneous or thermodynamically favorable, or if energy needs to be added, which would make it non-spontaneous or thermodynamically unfavorable. And this was proposed by this guy, Josiah Willard Gibbs. All right, and you'll recognize the equation here. Delta G is going to be the sum of the free energy of formation of the products minus the sum of the free energy of formation of the reactants. So this looks a lot like our enthalpy equation from Unit 6. And the delta GF, like I said, is the free energy of formation. This is the free energy associated with the making of a compound from its pure component parts. And this will usually be on a table. And also, like the enthalpy, the delta G of formation of pure substances is always going to be 0. And one interesting note about delta G is that for phase changes, when we're at the phase temperature, like if we're at 0 degrees Celsius, we're looking at the freezing / melting point of water, there's going to be a zero free energy here. Because if you think about ice or water at 0 degrees Celsius, it's not really going to be pushed in one way or the other. Being exactly at zero doesn't mean it's frozen or it's melted. It's sort of on that brink in between them. And if you were to move the temperature in either direction, it would favor one of those states. So since it's teetering there on the edge, neither of those states is necessarily more favorable than the other. And when we're looking at the delta G overall, a negative delta G corresponds to a reaction that is thermodynamically favorable, so one that is likely to proceed in the way that it's written, kind of like being product favored when we talk about equilibrium. And we'll work equilibrium into this later. And then delta G being positive means it's thermodynamically unfavorable, which means the reaction as written doesn't want to proceed as written. It's going to be more reactant favored. And if delta G is equal to 0, the reaction is at equilibrium, because at that point, there's no push towards one side or the other. We have balance between the products and the reactants. So a quick note here is sometimes you'll see the word spontaneous associated with something with a negative delta G. And this means the same thing as thermodynamically favored, but the College Board prefers this as the terminology to use. So you'll see spontaneous pop up a bunch, but when we're talking about it on the AP exam, please make sure to use the words thermodynamically favored. And the reasoning for this is because the word spontaneous is usually associated with something like sudden or unprompted, like you made a spontaneous decision to go do something one day. And that kind of sudden and unpromptedness, or that sort of randomness that we might refer to when we say spontaneous, is not how this works in chemistry at all. So that is the reason why we don't use that word to describe this for the AP exam. So overall, the universe tends to favor low energy and high disorder, which means that a exothermic process is generally favorable because it's going from a higher energy to a lower energy. It's letting the universe relax a little bit. And an increase in disorder is also preferred. And this is something you might see in your everyday life of, you spill something and it scatters everywhere and makes a big mess rather than, spilling into a nice even pile. And delta G, the free energy, which is going to predict whether something is likely to occur or not based off of thermodynamics and the universe's preferences, can be related to delta H and delta S, and also the temperature. And the equation that relates these three values to each other are delta G is equal to delta H minus T delta S. You'll remember that in the delta S units, there was that Kelvin bit, so this temperature also has to be in Kelvin. And you can see that delta S is linked to the temperature because they're so correlated with each other. So delta H, like we've seen before, is usually given in units of kilojoules per mole. And like I said earlier, delta S is in joules per mole per degree Kelvin, which means that if we're doing some calculating and we're trying to get a value for delta G, we need to make sure that all of our units in the equation agree. And the best way to do this is usually just to convert our entropy into kilojoules per mole per degree Kelvin rather than joules per mole per degree Kelvin. So we'll want to just divide it by 1,000. So you will be responsible for doing calculations with this equation, but there's another way of using it more qualitatively by looking at the signs of the different state functions. And this can actually tell us a lot about the chemical equation qualitatively. So for example, let's look at our thermodynamically favorable situation, or at least the universe preferred situation, where we have an exothermic reaction and a reaction that increases in disorder. Well, based off of the equation of delta G equals delta H minus T delta S, that means we're going to have a negative minus a positive. And if you think about just common arithmetic, a negative minus a positive is always going to be a bigger negative. So this process is always going to result in a negative delta G, aka a thermodynamically favorable situation. And it doesn't matter what the temperature is, it's always going to get negative. Now, if we look at the opposite end of the spectrum, if we look about the non-universe favored situation of being endothermic and increasing in order, that would be a positive minus a negative, which is always going to be a bigger positive. So there's no circumstance in which this wouldn't be a thermodynamically unfavorable situation or a positive delta G. Now, if we have endothermic and increase in disorder, now this is going to depend on the temperature, because if we have a positive minus a positive, it's really going to matter which one of those two positives is bigger. So at lower temperatures, the entropy is usually going to be smaller than the delta H term. So if you have a positive minus a smaller positive, that's usually going to result in a positive delta G. But if we turn the temperature up and our a second value in the equation becomes bigger than our first, then we're going to end up with a negative delta G. So if they're both positive, it's going to be highly dependent on the temperature, and high temperatures are going to produce a more favorable situation. Now, if we have two negatives, on the other hand, we're going to have sort of the opposite arithmetic, where we have a minus minus a minus. So in that case, you want the first minus to be bigger than the second minus if you want the value to still be negative. So in this case, it's going to be the opposite of the last one, where the lower temperatures are going to produce a more favorable reaction because it's going to keep the second term in the equation smaller than the first term. But if the temperature goes up, this second term is going to get bigger, and then we're going to subtract a bigger negative from a smaller negative, and we're going to end up with a positive value overall. So just a review here, exothermic and increasing in order is always spontaneous. Endothermic and decreasing in disorder is always non-spontaneous. Two positive is going to be dependent on the temperature, higher temperatures leading to more favorable reactions. And then for both negatives, it's also going to depend on the temperature, and lower temperatures are going to result in more favorable processes. All right, so let's try a little bit of conceptual practice here. Let's see if we can evaluate or predict the signs of the different state functions given different situations. So we have rusting, which it tells us is spontaneous and exothermic, ice melting, which it tells us is spontaneous and endothermic, and the removal of sugar from a cup of coffee, and it tells us this is non-spontaneous. So for the rusting situation, since it's spontaneous, or aka thermodynamically favorable, we know that's a negative delta G. It's exothermic, which means a negative delta H. And for the entropy, we can think about what's happening in the process. We have iron metal combining with oxygen gas to make iron oxide solid. So we have a different metal and a gas combining to make a single solid. And to me, that sounds like an increase in order or a decrease in disorder. So I would say this is likely a negative delta S. But we could do some more studying with that based off of temperature to see if this is really true. For the ice melting, it's spontaneous, aka negative delta G, endothermic, which would be positive delta H. And for the delta S, it's a solid becoming a liquid, so that's usually going to infer to be a positive delta S. And since it's spontaneous or thermodynamically favorable, and this is a phase change, we can assume that it's above the melting point, because otherwise the delta G would be 0. But the fact that it is negative means that we're probably at a higher temperature, and we're not at 0 degrees Celsius. For the removal of sugar, it's non-spontaneous, so that's going to mean delta G. I can infer that it's going to be a negative delta S because we're going from something that's dissolved into a solution to something that has been pulled out of that solution is now solid. That's a really hard thing to do. And we're going from a more disordered state of matter, being aqueous, to a more ordered state of matter, which would probably be solid if we were to remove the sugar from the coffee. So that's going to be a negative delta S. And then for delta H, this one's kind of tricky here. We would definitely want some like experimental data here if we were somehow able to do this experiment based off of temperature. But most dissolution processes are endothermic, because if you think about dissolving things, usually if you increase the temperature, it'll make it more soluble. So we can infer that most dissolution processes are going to be endothermic. And since this is the opposite of a dissolution, we can kind of infer that it's going to be exothermic. So in this case, delta H is likely to be negative. All right, now let's try to do the same thing, but with a chemical equation. So it says the reaction above is exothermic, and it asks us, is this thermodynamically favorable? Well, exothermic is going to mean negative delta H. So if we can figure out what the sign of delta S is going to be, we can determine what the sign of delta G is going to be based off of the relationship between them. So let's look at the equation. We have all gas. We start with 4 ammonia and 5 oxygen, combining to make 4 nitrogen monoxide and 6 water. And that looks like we start with 9 moles of gas and end with 10 moles of gas. So since we're increasing in our moles of gas, that would likely be an increase in disorder or an increase in entropy. So that's going to be a positive delta S. And if you recall, negative delta H, positive delta S, that's the best possible combination to get a favorable process. So we can infer that in this case, since we have a negative minus a positive, that delta G is going to be negative under all circumstances. So this is always going to be a thermodynamically favorable reaction, regardless of temperature. All right, now let's try to evaluate a process quantitatively. So here we have sort of a dissolution of ammonium nitrate in water, making aqueous ammonium and nitrate ions. And we're given the enthalpy and the entropy of the reaction. So it's 28.05 kilojoules per mole for the enthalpy, so it's endothermic, and it's positive 108.78 joules per mole per degree Kelvin for the entropy, so it's increasing in disorder. And we want to calculate delta G at 25 degrees Celsius. So we're going to use our formula for this. We can plug in our enthalpy directly. For the delta S, since it's in joules per mole per degree Kelvin, we're going to want to convert that to kilojoules so that the units agree. And don't worry about the Kelvin. That's going to get canceled out by the Kelvin in the temperature because delta G is going to end up being in kilojoules per mole. Which also means we need to convert our 25 degrees Celsius into Kelvin as well. So we're going to end up with 28.05 kilojoules per mole minus 298 times 0.108 kilojoules per mole per degree Kelvin. Remember that we converted this into kilojoules. And we end up with negative 4.134 kilojoules per mole. So overall, this is a thermodynamically favorable process. We can also use this relationship between state functions to predict the boiling point or the melting point of a substance if we know its standard enthalpy and its standard entropy for the phase changes, for the fusion or vaporization like we saw in Unit 6. So this is based off the fact that for a phase change at the melting or boiling point, the delta G is always going to be 0. So we can set it to 0 in the equation. And then we have delta H minus T delta S is equal to 0. And we can solve for T, which will end up being delta H over delta S. And we can use this to predict the boiling point of a substance if we knew the enthalpy of vaporization and the entropy of vaporization, or the enthalpy and entropy of fusion if we were looking for the melting / freezing point. So let's calculate the boiling point of water. I mean, you probably know it's 100 degrees Celsius, but let's see if we can get that value by using the entropy and the enthalpy. So our enthalpy of vaporization is 40.65 kilojoules per mole, and our entropy is 108.9 joules per mole per degree Kelvin. So if we set the delta G to 0, solve for the temperature, then we can just divide the enthalpy of vaporization by the entropy of vaporization, converted into kilojoules per mole so that the units agree. And then we end up getting kilojoules per mole, canceling out kilojoules per mole, and then 1 over degrees Kelvin, which is going to be degrees Kelvin, which gives us 373.3 degrees Kelvin. And we convert that back to Celsius by subtracting 273. We end up with 100. So we do get our predicted boiling point for water. So I mentioned before that delta G being negative and a process being thermodynamically favorable tells you whether a reaction is going to proceed as written from like reactants to products, and how that is similar to a product favored reaction in a reversible equilibrium system. And there actually is an equation that can connect delta G to K, the equilibrium constant. And it's as shown here. We have delta G is equal to negative RT ln K, where K is our equilibrium constant, T is our temperature in Kelvin, And R is sort of like a variant of the gas constant. It's also sort of an energy constant, but it's 8.314 joules per mole per degree Kelvin. So this way we can solve for the delta G of a reaction if we know the K for the equilibrium. We can also do it the other way around, where if we just use some algebra to rearrange this, we can have K is equal to e to the negative delta G over RT power. And because this is a natural log, the bigger K is going to be, the more negative delta G is going to be. And if it's product favored, it's going to be thermodynamically favorable because K is going to be greater than 1. And if it's reactant favored, it's not going to be thermodynamically favorable because K is going to be much smaller than 1. And the closer to 0 we get, the closer K is going to be to 1 in a situation where there isn't really any push towards one side of the equilibrium or the other. So let's try a practice with this equation. Say we wanted to calculate delta G for the following process at 298 Kelvin. And we're looking at the acid equilibrium of the dissociation of hydrofluoric acid. And we have an equilibrium constant of 6.6 times 10 to the negative 4. So we're going to plug everything into our equation. And it's going to be pretty straightforward, except for the one thing that we do need to note is that the constant is in joules per mole per degree Kelvin. So the value we're going to end up with is going to be in joules per mole. So we have our RT times ln of K. We end up with 18,144 joules per mole. And if we wanted to convert this into kilojoules per mole, we just divide it by 1,000. And we'd end up with 18.144. And this would make a lot of sense that we have a very positive delta G because we have a very small K. This will be reactant favored, therefore not very thermodynamically favorable, and we'll end up with a pretty high free energy that we need to put into this system in order to make the reaction proceed as written. All right, let's try another one. So say we wanted to calculate delta G for the following process, also at 298 Kelvin. So we have 2 nitrogen dioxide becoming 2 dinitrogen tetroxide, and we have a KEQ of 2.2. So this is a little bit more of a product favored reaction. So we could predict that this is probably going to be a negative delta G. So as usual, we can plug everything in, and that's going to look like this. So we have negative 8.314 joules per mole times Kelvin, or per degree Kelvin, times 298 times ln of 2.2, and we end up with negative 1,953 joules per mole, aka negative 1.953 kilojoules per mole. So slightly favorable and a slightly favorable equilibrium constant. So now let's try one where we know delta G, but we don't know K. So we want to solve for the Ka of hydrocyanic acid as it dissociates. So we know that the delta G is 52.5 kilojoules per mole. So very large positive delta G, which indicates a non-thermodynamically favorable reaction, which means this is probably going to be a very weak acid. So we're going to set up our other equation where we've rearranged it to solve for K. So it's going to be K is equal to E to the negative delta G over RT. You'll notice here that I changed my 52.5 kilojoules per mole to 52,500. That's because our constant is in joules per mole per degree Kelvin, so these units need to agree. So then I divide that by RT, and then I do e to the negative power of all of that, and I end up with 1.61 times 10 to the negative 10, which is a very small equilibrium constant, which agrees with my previous prediction that this was going to be a very weak acid. So sometimes you'll run into a process that appears to be thermodynamically favored based off of the signs of its state functions, but will either occur really, really slowly or will be observed to occur to not a real significant extent. And these types of reactions are said to be under kinetic control, meaning that it's being sort of limited by the kinetics of the situation. Now, a primary reason for this is usually because of high activation energies. Say we were to compare graph A to graph B. These are both exothermic processes, which are both somewhat thermodynamically favorable. You know, it still depends on the entropy. But for A, we have a very small activation energy, and B has a very large activation energy. if you remember from our unit on kinetics, when two particles are going to react, they need to collide with the right amount of energy and the right orientation. So there's these specific things that need to happen for the reaction to proceed. And this is going to be sort of a mechanical thing that isn't really related to the before and the after state. It's sort of like in the in between. Now, in this case, reaction B is going to occur much less than reaction A, because for reaction A, it can kind of just slip over this hill as long as it can get that slight little bit of energy to proceed. Whereas here, it's going to need to get a significant amount of energy and be in specifically the right circumstances in order to proceed to the products. So a good example of this is most combustion reactions. So let's consider the combustion of propane. So we have propane plus 5 oxygen molecules making 3 carbon dioxides and 4 water molecules. And this is highly exothermic. But if we look at the entropy here, let's see, we have 1 plus 5, 6 moles of gas becoming 7 moles of gas. So that means that is a positive delta S. So negative delta H, positive delta S, that's one of our always thermodynamically favorable situations, because we're always going to end up with a negative delta G. But if you have some propane lying around with some oxygen surrounding it, it usually doesn't randomly combust into flames. And that's because there's probably going to be a high activation energy for this to occur. And that makes sense if we think about how we burn propane in the first place. Either we need to have some sort of ignition process that uses a spark, or use a match to light the gas on fire. And both of those examples are going to be providing that energy to get the process over the activation energy hump to proceed in the first place. All right, so that is all I have to talk about for part 1. So I'll see you in part 2.